Wonderful to have you all over here. Thank you. So, first of all, what I realize is that I'm speaking to the right set of audience. Exactly the right set of audience because I'm looking for first year students, second year students, and students in MSc who can participate in some of the projects or projects similar to those which I will be describing. You look at the pictures of these students, they all started working with me when they were in the first year of their college after finishing 12 years of high school. So they're almost exactly at the same level. Okay, you are exactly at the same level. The first one is Parth, second is Aviya, then we have Vishwanath, and then Kaushal, all first year students. So you must connect yourself to them immediately. First of all, you should know that I'm talking about people who are like you, which essentially means that you can do what they have done. And I'm going to tell you the full story. But the first thing I want to mention is that they started working with me in their first year. They progressed through the second year. And by the time they came to the third year, all of them have published a paper in a journal. All of them. Some of them have published, and it is very exciting to see your name in print in a journal. And they have this privilege at the age of, they come to the first year around the age of 18. By the time they're 20, they have their first paper. And there are faculty members over here. I'm sure that they would have all published papers in some or the other form. But will some of you like to share your experience and tell me what was your age when you published your first paper? Can some of the faculty members? 25. Anybody else? 23. 23. Anybody else? 26. 26. So, I myself was, I think, 25 or so when I published my first paper. 25 or maybe even 26. And most people do this around 25, 26, thereabout. Whereas these kids, they did it at the age of 20, 21. So you get a 4 or 5 years of head start compared to those who have achieved quite a bit in their lives. So many of these have gone ahead and done various things. So the rightmost is Akash. This picture has been taken in my apartment in Tirupati with my research collaborator Sriram Malluri from the University of Western Ontario in Canada. And Akash is now studying in the US. The picture next to him is Vivishek Sudhir. I should tell you Vivishek's story. Vivishek was a first year engineering student at the Amrita University at Coimbatore. Some of you might have heard about it. He was a student of electrical engineering. He went to his physics teacher, Subhish. Subhish had done his master's at IIT Madras. He was my student. So Subhish knew me very well. And Vivishek went to Subhish and said that, sir, I'm interested in physics. Can you suggest some projects? So Subhish made a few suggestions to him. And then after 2 months, Subhish called me and said, sir, I cannot handle this boy. He is over enthusiastic. Can you guide him? So Vivishek traveled at his own expense. He came from Coimbatore to Chennai. I was teaching at IIT Madras at that time. And he told me about his interest. I found accommodation for him in our IT hostel. We shared accommodation with one of my other students. And his first few visits were like this. He kept coming. Then for longer visits, sometimes on vacations, weekends, and so on. And his background was no more than what an average high school student has. So I started introducing him to mathematical methods, classical physics, electrodynamics, a little bit of quantum theory. What is Sumesh doing now? He published two papers before he finished his Bachelor of Engineering from Amrita University, but went on to do physics because he got a start. He got a start at the age of 18. And today he is one of the world's leader in demonstrating quantum effects on macroscopic objects. Okay, when you talk about quantum theory, most people believe that, okay, this is a theory about microscopic particles, elementary particles, very small objects, and so on. But the fact is that it is a universal theory. There are no exceptions. Large objects, the reason this bottle is sitting over here, this is a macroscopic object, right? It is not falling through this desk. And there is a simple reason that gravity attracts it downward, but the table is holding it. What is this process of holding? There is a normal reaction. But what constitutes normal reaction? Normal reaction is only a name. There have to be physical interactions which are involved in this, okay? And there are only few physical interactions that you have to learn about in physics. Gravitational interaction, electrodynamic interaction, nuclear strong, nuclear weak, you're all aware of it, right? Yes. Now if you put all of this together, you cannot generate sufficient normal reaction to hold the bottle. If you do an exact calculation, it will turn out that you cannot explain even the equilibrium of why this bottle is standing on the table, or why you are not falling through the chair. And these are all macroscopic objects. And these are some of the quantum manifestations, but then these are not really measurable. And there are very few experiments done anywhere in the world in which you can actually show how these quantum effects can be measured. And Vivek Sudhir now works at the Massachusetts Institute of Technology. He is one of the world leaders in this business. I'm going to tell you about some of the others also. They all started in first year. And if you begin now, you can be where these go. Some of them are no longer kids. They have become senior. If you recognize that I am hundreds of years old, my students will not be like in 20s now. Because I have been teaching for I don't know how many thousand years. Right? So some of them are now very distinguished scientists. They are in top organizations in the world. Some of them are professors, scientists in some of the leading institutions. And I'm not talking about an exception. How many do you count here? And this is not the full list. This is illustrative of my very rich experience of working with undergraduate students. I could not accommodate more pictures on a single slide, but there are more. So let me tell you about some of this. First thing to recognize is that science is very young. It really is. But the pace of development is extraordinary. The world is more than 13 billion years old. Science is just a few thousand years old. Okay, even if you go back to the times of, you know, Aryabhatta, Archimedes, and so on, it's still just a couple of thousand years old. Modern science, people all often say that what we call as modern science sort of began with Galileo, Newton. These are also a few hundred years old. Quantum mechanics is not very young anymore. It is already 100 years old. The so-called quantum computing, which I am sure everybody has heard about. Quantum computers are being built, and right now there are only few quantum computers in the world, but in another 5 or 10 years there will be many more. And they will change computing even using classical algorithms. So it is important that your generation really latches on to this very fast, because although science is young, the pace at which it is progressing from 2000 years ago to a few hundred years ago to now what is happening in the last 100 years, and now what is happening in the last 10 years, the last 2 years, and what is happening even as we speak, there are advances which are absolutely stunning. So look at this picture. You have the Earth spinning about its south-north axis, right? But you will notice that if you are in a hall like this, okay, the hall, this has got a certain shape, okay, and wherever you are on the surface of the Earth, being spherical, the northern edge of the floor moves eastward slower than the southern edge. Now, in this hall, I have not come earlier, so I'm not sure which is north and which is south. Over here, this is north. Okay. So everything is spinning, right? Even as we are sitting here, everything is spinning. But do you see that the northern edge is spinning slower than the southern edge, because the southern edge has to travel more distance in the same time to complete 360 degrees in 24 hours. Are we all together? So this has got some very exciting consequences. If you now throw a projectile from the North Pole, okay? Let's say it is an intercontinental ballistic missile, and your target is on the equator. Now the missile, after you fire, is not going to get there instantly. It will take some time. And as it travels, the Earth would have rotated. So would it not miss the target? Right? You understand that? And this will happen in any war. Even if you are firing a bullet, okay, your target is on this wall, and you're firing from here, from this wall. Okay? By the time the bullet travels, the Earth would have rotated a little bit. And depending on whether you're firing toward your east or west, or toward north or south, you will have to carry out a very detailed correction to how you should aim. Okay? So these things are very important. And think about planes which are flying from, let's say, Mumbai to Kolkata. Okay, what's happening in between? A flight from Bangalore to Delhi takes 2.5 hours. Through how much angle would the Earth have turned in 2.5 hours? It's not a small hours, right? In 24 hours, it completes the full rotation. So in 2.5 hours, it is 1/12 of that, almost, right? Something like that. So now, all of this are very important factors. As a matter of fact, there is a Battle of Falkland that you can read about on Google, in which the British shots landed about 100 meters to the left of the target in the World War. So these things have actually happened, and they have had consequences in warfare and in many other things. Also, I just illustrated a few examples. Now think about an earthquake. Now what happens in an earthquake, or for that matter even in a landslide? There is reorganization of mass. A bit of mass moves from one part to another. That's actually happening even when we are walking. Okay, when I walk across, some bit of mass distribution has changed. And I know I am a fat man, but it is not so significant. But when an earthquake takes place, okay, or when there are landslides on mountains, some of the big ones, the mass distribution changes quite significantly. So we are talking about the Japan earthquake in 2011. This was a 9 Richter earthquake, and there are such earthquakes that you hear and read about all the time. And because of the mass distribution, what happens now? The mass distribution has changed, so the moment of inertia will change. Moment of inertia depends on how mass is distributed, right? So the moment of inertia changes. Angular momentum is a constant, but the moment of inertia has changed. So what will have to change? The angular speed, right? So it cannot complete 360 degrees in exactly 24 hours. There will be some difference. It will be small, but it will be there. And that difference is 1.8 microseconds as a result of the earthquake. Now, how serious is this 1.8 microseconds? Yes?
नॉर्थन हेमिस्फीयर और साउथर्न हेमिस्फीयर का तो हिस्सा को
बिल्कुल बिल्कुल है, बिल्कुल है।
वो रोटेट कर रही थी।
हाँ,
तो बेंड तो ठीक है, लेकिन
नहीं बिल्कुल है। तो ऑब्जेक्ट की जो
डायरेक्शन
डिफ्लेक्शन होता है, वो नॉर्थ में जो ईस्टवर्ड डिफ्लेक्शन होता है, वो साउथ में लेफ्ट वेस्ट में होता है। You're right. So let me tell you how important it is. The New York Stock Exchange had to be stopped. I think there is a date given there, 30th June 2012, which is just a little more than a decade ago. Because trading is done on the stock exchange, and if trading begins at 9 o'clock in the morning in New York, the atomic clocks all over the world must be synchronized. The time is different in different time zones. 9 o'clock in the morning in New York would be like 6:30 in the evening in India. It would be maybe 10:30 late evening in Australia, and so on, right? So these are different timings in different parts of the world. So all of these timings have to be synchronized, because in a fraction of a second, exchange of billions of dollars takes place. And because these clocks were not properly synchronized to take into account the rotation of the Earth, the stock exchange actually had to be suspended on 30th of June 2012. So subsequently, they started incorporating this correction. Like every year, every 4 years, you know that there is a leap year correction. That is for astronomical reasons, but there is this correction which is called the leap second correction. And it is because of this reason which I just mentioned. So people do this, and the reason to mention it is that Gopal Pandurangan, who was a first year student, he's now a professor of computer science at the University of Houston. Okay, so I'm going back to the days when Gopal was a first year student, just like anyone sitting here. And there are some detailed calculations which have to be done. Not very difficult. All you use is differential equations. A good bit of physics can be done with differential equations. And I'm sure all of you have studied those, right? Everybody knows the second order differential equation?
Yes, sir.
How do you solve it? Essentially, you have to integrate the equation, right?
Yes.
And every time you integrate, you have to pick up a constant of integration. But you have to pick two constants of integration because you have to integrate it twice. And then you plug in the constants of integration, you'll get the solution. So you have to set up the correct equation of motion, the correct differential equation, which is somewhat complicated in this context, but nothing beyond the reach of a high school student. Okay, some of you may already be familiar with this. Gopal studied this equation, solved it, generated a numerical code to solve the differential equation with appropriate boundary conditions, initial conditions, and so on. And then we published it in a journal a little bit later. Does it not excite you? You can do it, okay? All it needs is the same background with each one of you has. And you can do it, publish a paper. He's now a professor of computer science at Houston. I was asked to give this talk, Gravitational, a few years ago, and by the Cambridge University Press, which published my book. And they asked me to give this talk, at which time I got in touch with some of these students and asked them to send me a few remarks on their experience, to share their experience. Because in as much as I want to share with you my experience, I want to tell you about their experience. Okay? This is the note which I got from Gopal. This is almost 30 years ago. But this project was one of the best things that happened to me at IIT Madras. Okay? So IIT Madras is a great institution. He would have taken many good courses, many exciting courses. He would have learned so much. But he says that this was the best thing that happened to me, happened to him at IIT Madras. And what we did was we built a simulation code which Gopal developed. We used it in undergraduate laboratories. Gopal is aware of it. And he goes back to say that this was his first research experience and it played a role in me getting into full research career later. So this can be a turning point in your life. I want you to hear from Gopal himself. I asked him to send me a video clip. It's coming here.
Second one.
Huh?
Second one from here.
This one?
This one. देखिए आवाज के लिए
this is a project one of you can take up as to why the sound does not come and how to test it before you have such a demo. So that's Gopal who is talking to us. He recorded a small clip and I thought that I would share it with you.
So, but nonetheless, when I started, sir, जब मैंने अपना करियर शुरू किया, I also started in engineering college.
Yes.
और मेरे जो co-guide थे, उन्होंने किसी टाइम पे मुझे कहा, योगेश, फिजिक्स के जो प्रोफेसर है वो इंजीनियरिंग कॉलेज में जिंदगी में स्ट्रगल करते हैं, लेकिन मैं अपने आप को एकलव्य मानूंगा सर, आपकी तरह फिजिक्स का आदमी जो इम्पैक्ट जनरेट कर सकता है, नॉट ओनली फिजिसिस्ट बट बाकी लोगों के लिए, जो आदमी फर्स्ट ईयर में बच्चे से इंटरेक्ट करता है, चाहे वो केमिस्ट्री का हो, चाहे वो मैथमेटिक्स का हो, चाहे वो बायोटेक्नोलॉजी का हो, सर फिजिक्स की बात इसलिए कर रहे हैं बिकॉज ही इज ए फिजिसिस्ट. अदरवाइज ये जो इम्पैक्ट जनरेट होता है इनिशियल ईयर्स में, जो टीचर्स स्टूडेंट्स के साथ इंटरेक्ट करते हैं, उनका इम्पैक्ट लॉन्ग लास्टिंग रहता है. एंड दैट इज व्हाट इज इम्पोर्टेंट फॉर ऑल ऑफ अस. या तो वो लोग जिन पर इम्पैक्ट होना है, या वो जो लोग जिनको इम्पैक्ट जनरेट.
In undergraduate, when you're doing your undergraduate, is a great way to get into research, to talk and interact with professors and other students.
Yeah, now we will re-listen.
Remember, probably one of the few things that I really recall fondly from my undergraduate days at IITM. So I think doing research projects in undergraduate, when you're doing your undergraduate, is a great way to get into research, to talk and interact with professors and other students.
Great. So let us clap.
So there are a number of projects and number of students who have been involved in this, and I'm going to share a few examples with you. I'm going to talk about a project in which the principle of radiation is involved. Now, the principle of radiation is a very remarkable principle. Feynman developed a method which is equivalent to Schrodinger's method and Heisenberg's method of quantum mechanics. And he developed this method, this is called as the path integral approach to quantum mechanics. And Feynman tells us that he was introduced to it when he was in the high school. When he was in the high school, he had a teacher by name Mr. Bader, B-A-D-E-R, Bader. And Mr. Bader once found Feynman sitting bored. He said, "You look bored. Let me tell you something interesting." And he introduced him to the radiational principle. Later on, Feynman went on to develop the path integral approach to quantum mechanics and turned out to be one of the most distinguished contributors to modern physics in his times. Now, if you want to learn the principle of radiation, a good way to learn it is to think of some problems in which this is of importance. So let us take one example. I've got an object here, and I've got some sort of a slide. If I have a slide, a plate from here to here, so I'm going to release this object over here, and it will end up coming here. It will slide along the slope, right? But the slope can be either a straight line like this, it can be curved like this, or it can have a deeper curve like this, You get it? You can imagine these shapes?
Yes, sir.
So now, a question can be posed that if I drop a marble from here and I want to catch it here, I just release it. I don't push it or anything. It starts with absolutely no applied force under gravity alone, but the motion is constrained by the slope. And now the question is, can you tell me what must be the slope so that this marble will reach this point fastest?
The second one, the curved slope.
Which curve? I can draw infinite curves between these 2 points. I can.
Not so much deeper, but a curve which look like that.
I want an equation to that curve because there can be infinite curves between these 2 points. Just take a piece of paper and draw.
Straight line.
No, sir.
Yes.
Not a straight
So you understand the question? Do you realize that it is a tricky one? Now this question was posed by Johann Bernoulli. Okay, Bernoulli posed this question. It was a challenge question. And the challenge was that anybody who solves this problem would be worthy of Bernoulli's praise. No award of $100,000. The award that he would be worthy of Bernoulli's praise. So now there couldn't be a bigger award. Just think about you're being praised by Einstein or somebody like that. Right? So this was the award. And it was not easy to solve, but there were a few solutions which were offered. And one of the solutions was given anonymously by someone. He sent it to a friend and he said that you announce the solution, but don't tell that I have produced the solution. So the solution was tested. It was correct. And Bernoulli said that I can recognize the lion by its paw. This solution could have been only given by Isaac Newton. It was Newton's solution. So brilliant minds are involved in this. So now you understand how difficult this problem is, and it takes brilliance to learn these techniques. But you can learn these methods as high school students, as undergraduate physics and engineering students. And this is based on the principle of variation. It is also fundamental to quantum mechanics, not just the Schrödinger or Heisenberg formulation, but Feynman's path integral approach. And now you see 4 figures over here. There you have different shapes. So this model was constructed by first year students. I showed you the pictures of Parth and Abhiya earlier on the first slide. Abhiya is, I think, now doing mathematics. Parth is doing engineering. So they're not doing really physics as such. They're doing science, engineering, technology at different levels. And they fabricated these models. This is a very sophisticated experiment, but a very simple one. You can set it up in your lab. It will cost a little bit of money, but I'm sure your college can afford it. It will be a few thousand rupees or something. It's not like a huge amount of money. And what you do is you drop a marble at the top and then let it roll down along different shapes. And then you have to click the timing carefully. So there are certain photo detectors and so on which these people use for accurate time measurement. And they published an article, Vaishak, Abhiya and Parth. This article was published in Resonance in the year 2017, which was not too long ago. Let's see what Parth has to say about it. Come on, Parth. speak to us.
The journey of building the model and learning theory behind the Blackstone model was very exciting but as well as challenging at the same point. And building model was a really laborious task and but also satisfying at the same time because when you overcome the experimental hurdles you feel good about it. And this project taught me how to do experiment correctly and how what can be the challenges while while performing the experiment and how to write a research paper.
So this is really exciting. When first year, second year students get involved in projects of this kind, publish a paper, and then they reflect on it and tell us how it turned out to be it was a turning point in their life and it really made a huge difference for their careers. So this is based on the principle of variation. Now this is a worldwide, sentiment. I want to read out from the Council on Undergraduate Research. This was founded in 1978. This is an organization of individual, institutional, and affiliate members from around the world. Okay, everybody can be a part of this. Involve undergraduate students in research. And the mission of this Council on Undergraduate Research is to support and promote high-quality mentored undergraduate research, scholarship, and creative inquiry. So I hope that I will succeed in getting some of you to take up undergraduate research projects and publish them, and you can go a long way and get recognition for this. Now, here is another example. This statement is in a quote, so obviously I'm quoting somebody. Some of you might recognize who the author would be because some quotations are very famous, right? स्वराज्य मेरा जन्मसिद्ध अधिकार है. आप पहचान लेंगे कि किसने कहा है ना? So this quotation is also very famous. This is no other place in physics where such a simple and accurate general principle requires for its real understanding and analysis in terms of two different phenomena. And this is quoted, this is a quote from Richard Feynman. How many of you know Feynman? Not many. Not many. It's already late. It's already late. आज घर जब जाएंगे, thank you. आप आज जब घर जाएंगे, तो before you go to sleep, खाना वाना खा लो तबीयत से. But start listening to Feynman lectures. Okay? These lectures were given at Caltech by Richard Feynman to engineering students, not physics students, not science students, but they were taught at Caltech, which is an institute of technology, the California Institute of Technology. And 60 years after these lectures, they continue to inspire and educate generations of physicists, one after another. So yes.
So the first three lectures are very understandable for us people, but the fourth lecture and onwards are very complicated. When I watched them, I couldn't even comprehend at that time.
You do one thing, listen to it again, and then you will stop at some point where you have not understood that. Okay? After maybe 3 minutes, 4 minutes of the lecture, you think that you're not following it at that point.
Yeah, many times in the third lecture.
Okay, third lecture, whichever. Wherever you don't understand, stop there, write that question, send it to Yogesh Chandraji, send it to me, we will help. Okay? Okay? There is no other way to proceed. and don't deny yourself that privilege. You have that opportunity. Go to your teacher. Did you go to your teacher?
I just searched it up and didn't find
But
it.
you did not go to your teacher. And I did not stop you from going to your teacher. Okay? So go to your teacher. That is your first point of contact. Okay? And there are answers which every teacher will not be able to give. I cannot give many answers. I may not be able to answer all your questions. Then I will tell you that I cannot answer it, but I will put you in touch with somebody else. Right? What did I tell you about Subish? Vivishek Sudhir went to Subish. Subish said, I cannot handle it. You go to PCD. So you keep pushing, keep asking till you get the answer. I may not be able to give you that answer. I will refer you to Yogesh Chandraji. If he is not able to give you the answer, he will refer you to someone else, but will help you. That is the commitment we make here, right? We can't say that, okay, we will be able to answer all the questions. We don't know. We ourselves have limited knowledge. We are older than you, but we are still learning. So don't stop. So this is from Feynman lectures, and this has to do with certain things in electrodynamics. I don't want to go into the details, but you might have studied Maxwell's equations, you might have studied Faraday lens law and so on. So it is all based on high school physics and Faraday lens law and that. Nothing beyond it. But the reason to tell you about this is because Satish and Venkatesh, two pictures which I showed you on the first slide, they worked on this project, they studied it, and the related physics is very exciting and very deep. Why deep? Because it gives you the fundamental platform for the theory of relativity. It took the brilliance of Albert Einstein to discover. The special theory of relativity comes straight out of these equations, the Faraday lens law and so on. Okay? You know how important it is. Is there anybody you know who has not heard of the special theory of relativity? Who has not heard of Einstein? You know, all of you know it, but do you know anybody who does not? Anybody who has gone to school or college would know about Einstein and theory of relativity, right? That is how important it is. And that comes out of this. And what is this connection between Faraday lens law to the theory of relativity? That has been done by a simulation exercise by Satish and Venkatesh. Satish is now, both of them are in the US. Venkatesh is a professor at Stony Brook. Satish is, he's an entrepreneur. I think he has started his second startup. He is, I think, building driverless cars. Okay? But they all started with projects of this kind. Okay, so these are great guys. You often hear from students how much they learn from their teachers. I want you to know that as a teacher, how much I have learned from students. Students are a great resource. Okay, they have a huge amount of talent, huge potential, and as teachers, if we can, get them started on projects of this kind, they can go a very long way. So we will like both the students and the teachers to benefit from this. This is the remark over here. They say that when we look back at our undergraduate special project experience, we recognize that our project really helped us develop a foundation for lifelong passion for combining computation with theory in our own professional settings. So see how important this experience turns out to be. It has shaped our professional journey and careers in a profound way that we simply could not have imagined at that time. So you really can't imagine. But here, let me click on this. I think we are going to hear that.
What we think is that going forward, bringing theory and computation together will help us all solve a lot more of the problems facing humanity than what we have been able to do so in the past. And I now request my friend Professor Ventesh to say a few words about this as well.
Thank you, Satish. Of course, I also very much enjoyed working on the project as an undergraduate student. And little did I know that, the little experience that I had as an undergrad would inspire me and continue to keep me interested in understanding how computational approaches can be used to solve problems in the engineering and the scientific world.
Here is another one. These two girls, Jnaneshwari is on the left and Niharika on the right. They also came to be as first year students. And now think about the special theory of relativity. Don't you think it is somewhat of an advanced concept? Yeah? Do you think you can do an experiment in which you can see the effect of the theory of relativity? Have you done any experiment in which you can see the effect of relativity theory? In your high school or college? Will you like to do such an experiment?
Yes, sir.
Huh?
Yes, sir.
You can set up this experiment in your labs. And this is the experiment which was set up by Jnaneshwari and Niharika. Now this will cost a little bit of money because the apparatus this apparatus was not bought anywhere. This was fabricated in local workshops. And I can assure you that it does not require any sophisticated tools that you cannot access. You won't have everything that is required in your home, but you can certainly do it. You will need some help from your teachers or Yogesh Chandraji, or I can help you. Okay, you can set up these experiments. You can do an experiment in your lab. I think when we set it up, it cost us about 20 to 25,000 rupees. But it's not such a big amount that colleges do not afford. Colleges have that type of money. And we set up this experiment. This is a tabletop demonstration of relativistic time dilation and length contraction. There is this idea of time dilation. Time intervals are not the same for every observer. Length intervals are also not the same for every observer. And this is one of the essential consequences of the laws of nature, which are correctly described by the theory of relativity. So this can actually be demonstrated, the length contraction and time dilation, using some experiments. We actually published it in the IAPT Bulletin, Indian Association of Physics Teachers. You might have seen that paper. So what is Jnaneshwari telling us? It provided an opportunity to discover my abilities and help to improve my confidence, patience, and time management skills. Time management is important because this is not a part of your regular career, regular coursework. Okay, you will not get an improved grade because of this, but you will get an improved grade because of what you will learn while doing this. Okay, but you have to learn to manage your time, and all of these qualities, patience, because the experiment wouldn't work. We had to try it a number of times to figure out where we were going wrong and so on. But she learned all that. And this is a very rich experience.
We could see the decay cracks in the cloud chamber, which reveal many aspects of cosmic showers, including neon decay. In spite of many challenges, we could carry the experiment with outstanding success.
So this is really important because what is research is you have to learn certain topics in a systematic manner. You run into a difficulty, you don't understand, figure out what is going on, like what you said is very correct. You do get stuck. You will get stuck while listening to a lecture by Feynman on the YouTube. You will also get stuck while reading about any analysis in a book. You will come to equation number 22 and you will not be able to see how equation 23 came out of equation 22. You get stuck over there. Okay? And the only way to proceed is to go to your teacher. Ask your friends, try to solve it. Don't stop. Okay, have that much of willpower if you don't have, that you don't push yourself till you get the solution, you will not succeed. But if you want to succeed, keep asking. You ask one friend, he won't give you the answer. Ask another, he may also not give you the answer. Ask one teacher, another teacher. Don't stop till you get the answer. And if you can't find a teacher, send an email to Yogesh. He will answer most of the questions. If he doesn't want, if he doesn't have the time to answer, he will refer it to someone else. But as a team of teachers, we will find you the answer. So I talked about the special theory of relativity. Now I talk about the general theory of relativity. Okay? And this is important for why I'm here. Tomorrow you are celebrating the anniversary of the detection of gravitational waves. Okay, that's, I think all of these students will be part of that event. And the gravitational waves were predicted by general relativity. I will be talking a little bit about it in tomorrow's lecture. But it involved a very small correction. 43 arc second per century is like about a little more than 1 degree angle over 100 years. Okay? Can you draw a right angle, everybody? Pull out a piece of paper and draw a right angle. Roughly. Just draw a rough right angle, 90 degrees angle between two lines. Do it quick. Now draw a 45 degrees angle. Now a 15 degrees angle. Draw a 10 degree angle. Now draw a 1 degree angle. Use a protractor if you like. And if something is moving, okay, I have got a line, it is turning. Can you see how small an angle it is? Can you see how small an angle it is? And I've got a line which is turning through 1 degree in 100 years. How slowly this is turning. You get it?
Yes, sir.
So that kind of correction is involved because the previous theory, which was Newton's theory, was not correct. Some corrections were needed, and these corrections come from Einstein's general relativity. The same theory predicted the gravitational waves. I will talk about this more tomorrow. But today I want to mention in this context that this work was carried out by Kaushal. He is now doing his PhD in Australia on general relativity. But he started working on this when he was a first year student like anyone else. Okay, as a first year student, I asked him, I gave him this problem. I mentored him. I told him what are the mathematical techniques, the numerical techniques. He developed a code. We published this in Resonance. You will find this article on the internet very easily. It is Resonance in 2017, volume 22. It is called GTR component of planetary precision. The angle, the precision is the precision of the orbit of Mercury. But I will talk about it tomorrow. So today I don't want to spend time on that. And Kaushal did this work.
So research process is a step-by-step thing. First you think of an idea or come up with a hypothesis, then you test this idea or hypothesis using computer simulations or observational data, or you come up with a new experiment to test this hypothesis. Secondly, it also teaches you that failure is part of research. Sometimes your computer programs don't work, sometimes your experiment goes wrong, and that is okay. The important thing is to come up with new approaches using your knowledge and experience to tackle such problems.
Look at this one. Now this is when I was teaching about nonlinear equations. Okay, the theory of chaos. Have you all heard about the theory of chaos? Hmm? Have you studied it anywhere? Have you heard of the butterfly effect? So let me tell you what the butterfly effect is. तितली तो देखी है, पकड़ी भी होगी, है ना? कुछ तो निकल भी गई होगी. But when a butterfly flutters its wings, okay, the molecules of the air would have to move, right? And these molecules of the air over here, they will push the neighboring molecules. The neighboring molecules will push other molecules which are neighboring to them, and the effect can cascade. It can travel, become large effect at some level, okay? And because of the manner in which the butterfly has fluttered its wings over here in the garden outside, here in Jaipur, because of this butterfly effect, which is cascading and traveling, you may have a storm in New York. It actually happens. It actually happens, and you see this phenomenon in nature in a number of different situations. In a large number of different situations. Sometimes you see it in market exchange rates. There is some trading which is taking place, and $1 is so many rupees, 82.36978 or whatever. But sometimes there is some trading which is done which affects the market, that affects something else, which affects something else, and just like the butterfly effect, it cascades and the dollar falls. Okay? So these things have been found in economy, in electrical engineering, in civil engineering, in physics, in biology. How your heart attack can take place. Okay? Something small. You see a person who is physically fit walking around, everything is fine. And then suddenly you see that he has collapsed. So there are these butterfly effects that people experience in all walks of life. And this belongs to a theory which is the theory of chaos. nonlinear dynamics, fractals. Fractals talk about fractional dimensions. We talk about one dimension, second dimension, third dimension. We can expand this to 4 and 5 and 6 dimensions and so on. Fractals are about fractional dimensions. Okay, a dimension which is not two-dimensional object, an object which is neither three-dimensional object, but it has got a dimensionality between 1 and 2 or between 2 and 3. Because it is fractional, it is called as a fractal. And it is illustrated using what is called as a Menger sponge, and I talked about it in a first year class, and I told them that you can generate a model of the Menger sponge. You can do it using cardboards and glue. All you need is a glue stick and some cardboard sheets. Actually, you can see this. Yeah, these are just cardboard box. Okay, so you have to cut certain holes. All you need is cardboards, scissors, glue sticks. And the student got so excited. This picture is taken at night. The whole night, the whole class, they were building these Menger sponges using these cardboard boxes and scissors and cellophane tapes and glue sticks. They created, they built 3 of these models through the night, whole night they worked because they were very excited by this idea of a fractional dimension. And a Menger sponge has a fractional dimension. So you can do it. If you begin tonight, you will have it tomorrow morning. And it will not cost more than a few hundred rupees.
Increasing by the time that it reaches some
Not
places.
necessarily. Not necessarily.
It would be negligible.
That is what you think. But I just told you that the effect is real. Okay? I will be very happy to explain how this happens. You can think about it in a very easy manner. I'm sure this has, if it has not happened to you, it will. Go for a movie. घर में बैठ के मत देखो, थिएटर में जाओ, लाइन में लग जाओ टिकट खरीदने के लिए, हाँ? धक्का खाते हैं खाओगे, हाँ? जबरदस्त. तो आप जब लाइन में खड़े रहते हैं, okay, there are 100 people in front of you, another 100 behind you, और किसी का छोटा धक्का लग जाता है, right? And the धक्का travels through the line because everybody is standing next to each other. उधर किसी का बैलेंस निकल जाता है, वो गिरता है, उसके गिरने से एक मोटरसाइकिल गिर जाती है, वो मोटरसाइकिल गिरने से किसी की टांग टूट जाती है, किसी ऑर्थोपेडिस्ट सर्जन का उसमें कोई फायदा भी हो जाता है. आपने इतना छोटा सा धक्का
Like the
सोचा,
chicken crossing a road. That problem.
आपने शायद सुना होगा गाना, वो भिखारी भीख मांगता है, वो कहता है कि मुझे 10 पैसा दे दे, दिलाई दिला दे बाबा, दिलाई दिला दे, दिलाई दिला दे, नहीं तो तेरी नानी मर जाएगी, नानी मर जाएगी तो बमन बुलाएगा तो काशी को जाएगा, इतना जो करे बाबा दिलाई दिला दे. समझा? So this is the butterfly. Small things normally have small consequences, but not always.
The traffic problem that
Absolutely.
that is also butterfly.
Absolutely. Small things normally have small consequences, but sometimes you have non-linear effects. So small things causing large effects.
It is increasing.
And that can increase. So what you said is absolutely correct, but that is not the rule. But the exceptions are not few, and you see it in nature. You see it in a large number of situations. So these Menger sponge was built by this batch of students. Now, Abhiya went one step further. She was one of the students who built that Menger sponge. But then we took this idea to chemical reactions. And chemical reactions, you have A plus B, two chemicals you add, react, and then you get C plus D. But you can also have a backward reaction. Starting with C plus D, you can come to A plus B. And then depending on the reaction conditions, either the forward reaction will be faster or the reverse reaction will be faster. And depending on this, the reaction products will change. So some chemical reactions, they change in a very unimaginable manner. You make small change in the concentration of A, very small concentration. You just go from 0.39 to 0.395. In the third place of decimal, you make a small change. And the reaction product is so different that the color of the chemical in the beaker will be different. You see such brilliant colors, all shades. You see, you can do this experiment in your lab. Actually, this is one experiment they can certainly do in the chemistry lab. And by changing very small, making very small changes in the concentration, the consequences can be very large. That is just the idea. But here, what Abhiya did was to show it in chemical reactions. We published this 4 years ago in Resonance, Nonlinear Chemical Reactions, the comparison between experiment and theoretical model. She did some very nice experiments and also did simulation. So these are the advantages of undergraduate research. Develop critical thinking, creativity, problem solving, intellectual independence, okay, many things. So I think, how much time do I have? Yeah, so I will conclude now because I don't want to, but I hope I shared an idea. So I will be very happy to take some questions, but I will conclude here. We have a very busy evening. We have a very exciting evening. I want to hear. Yes. So Professor Yogesh has contributed a lot to exciting education, and more than anyone else, I'm eager to listen to him. So I will stop here, but I will be happy to take questions either now or you can send your questions to me later by email. तो मैं इसको बंद कर देता हूँ ये Yes.
Thank you very much, sir. Thank you for your talk and to share your information. Question नहीं है, थोड़ा सा एक comment है.
Sure.
Sharing or maybe something
Yes.
about rocket share करना था. I'm a biochemist.
Yes.
And I was eager to come here to listen to you. मैं सोच रहा था जब आप butterfly effect की बात कर रहे थे, तो ठीक है, फिजिक्स के लेवल पे कंटिन्यूटी और इस सब चीज़ों की बात नहीं आती, सिंक्रोनिसिटी की बात नहीं, जब भी आप एक लार्ज इम्पैक्ट की बात करेंगे. तो होम्योपैथिक ड्रग्स के बारे में अक्सर लोग ये मानना बोलते हैं कि भाई इतने कम डाइल्यूशन पे, इतने कम कॉन्सेंट्रेशन पे कोई इम्पैक्ट आएगा तो वो साइकोलॉजिकल होगा या प्लेसेंटल इम्पैक्ट होगा. बट इतने सालों से जो इम्पैक्ट लगातार जनरेट होते आ रहे हैं और लोग उसका फायदा भी उठा रहे हैं, तो बहुत सारी सोसाइटीज उसको एक्सेप्ट करती हैं, ड्रग के तौर पर बहुत सारी सोसाइटीज नहीं करती हैं. आई वाज जस्ट वॉन्डरिंग कि उसमें साइकोलॉजिकल और प्लेसेंटल इम्पैक्ट के अलावा हो सकता है उसका कंट्रीब्यूशन हो, बट आई वाज वॉन्डरिंग कि उसमें शायद बटरफ्लाई इम्पैक्ट से ही एक कंटिन्यूअस और सिंक्रोनिक इम्पैक्ट भी देखे जा सकते हैं. ऐसा मुझे फील होता है. बहुत सारे लोगों ने प्रूव करने की कोशिश की, बट कुछ हद तक कामयाबी भी हुई, डिजिटलाइजेशन भी का कोशिश किया गया, सिग्नल का फीड करके उसको रेसिप्रोकेट करने की कोशिश किया गया, बट देन एट द एंड इट वाज नॉट टेकन एज अ ट्रूथ. बट नाउ आई थिंक अगर इन तीनों इम्पैक्ट को मिला दें तो शायद होम्योपैथी एज अ ड्रग को और अच्छा.
Yeah, this is a matter of research. This is a good project for research. मैं इस पे स्पेकुलेट नहीं कर पाऊंगा.
मैं स्पेकुलेट कर रहा हूँ.
लेकिन आपकी जो सोच है उसमें there is a reason to research. इतना मैं आवश्यक है. So this is a topic for further research, and the results will be very interesting. But there are very important consequences, and possibilities are very many. And I will not be able to help you with the specific field, but the general theory of chaos and the general theory of nonlinear dynamics is something that I can help you with. Okay, so far as the tools are concerned, we can help you with the tools. Sure. Is there any other quick question? So,
Thank you, sir. Thank you very much again. So, मदर नेचर बड़ा एक डिफरेंट वे में सोचती है. उन्होंने इसको जो बनाया है ब्रह्मांड को, वो बड़े अलग तरीके से. और जैसा सर ने कहा, ये जो यूनिवर्स है ये तो लाखों हजारों करोड़ों सालों से है, और साइंस तो बिल्कुल नया है, जिसको हम साइंस कहते हैं. साइंस क्या? नेचर को समझने का एक तरीका, जिसने चीजों को चेंज किया. ये जो स्ट्रेटा हमारे सामने खड़ा किया सारा, it is very new and it is very young, but yes, yet we are successful. That is what recently मैंने ये कोट पढ़ा कि जिस तरह से मदर नेचर करती है, आदमी उसी तरह से सोच सकता है. We are in alignment with the mother nature. Quantum mechanics or these things, these theories which sir is saying, they again reiterates that yes, जो आदमी नाम की जो स्पीसी बनाई गई है, वो सोच सकती है, वो कर सकती है जो मदर नेचर. अगला जो सेक्शन है इस आज की इवेंट्स की कड़ी में, उसमें प्रोफेसर योगेश भटनागर साहब और इनकी टीम, इनके साथ लोग आए हैं. ये आपको बताएंगे कि क्या हम देखने वाले हैं, क्या हम करने वाले हैं. और उसके बाद आप लोगों को लीगो लैब, वो लैब जहां पर आइंस्टाइन की थ्योरी ऑफ रिलेटिविटी का एक्सपेरिमेंटल वेरिफिकेशन हुआ, उसका एक वर्चुअल टूर कराया जाएगा. सो मेरे ख्याल से दिस विल बी फॉर द फर्स्ट टाइम, जैसा जहां तक मुझे ध्यान है, इट विल बी फॉर द फर्स्ट टाइम. आई हैव नेवर लिसन. हमारे यहाँ एक प्रोफेसर हैं जो इसी पर्टिकुलर फील्ड में काम करते हैं, और इन लैब्स के डेटा को यहाँ पर रिसर्च स्टूडेंट्स के लिए उस डेटा को काम में लिया जाता है. इसी तरह दो चार लोग जो मेरे क्लोज टच में है, राजस्थान यूनिवर्सिटी के प्रोफेसर हैं, सेंट्रल यूनिवर्सिटी ऑफ अमरकंटक के प्रोफेसर है जो कल आ रहे हैं, उन्होंने भी उस डेटा को काम में लिया है. दे आल्सो ट्राई टू अंडरस्टैंड व्हाट इज हैपनिंग देयर, बट वो लैब अभी तक किसी ने देखी नहीं. सो दिस विल बी, आई थिंक, फॉर द फर्स्ट टाइम that we will be able to see that particular lab. That will be around 6. But उससे पहले का जो समय है, प्रोफेसर योगेश भटनागर साहब, he is also a very senior IAPT member, physics community member. जिस विश्वास के साथ पीसी देशमुख सर कह रहे थे कि अगर चीजें हमारे समझ में नहीं आएगी तो हमारे पास दूसरे लोग हैं जो इन प्रॉब्लम्स का सोल्यूशन हमें दे सकते हैं. सो इट इज ए कम्युनिटी ऑफ फिजिसिस्ट जो इस फील्ड में काम कर रहे हैं. उनका जो ज्ञान अपने पास है. सर इस उम्र में मेरी रिक्वेस्ट पर कल से या परसों से शायद दिल्ली किसी मीटिंग से आए हुए थे, सुबह जल्दी उठकर ट्रेन पकड़कर आप लोगों के लिए आए हैं, और अगले 2 दिन तक हमारे साथ रहेंगे. एंड ही विल बी एनरिचिंग व्हाट इज हैपनिंग हियर. सो थैंक यू वेरी मच सर अगेन for the session, and now I welcome Professor Yogesh Bhatnagar sahab on the dais.
Thank you, Yogesh sir. It was an opportunity given to interact with you, friends. Uh, Recently, we have been listening a very serious lecture about the relativity, general theory of relativity, some new concept, some practical aspect that the Professor Deshmukh sir was able to pass to us and incite us to do something in the field which is completely unknown to us at the moment, and in which lots of the people are trying their energy and their time to find out the future of this one. My field is a bit different. I'm taking the lighter aspect of the astronomy. We have always been a very serious aspect. We have learned about the relativity, the quantum dynamics, quantum theory, quantum mechanics, and so on. I'm taking the lighter one aspect, how we can, because sometimes it is not necessary you have to be a very serious to learn something. Sometimes in your usual way, आप अपने नॉर्मल तरीके से भी आप अपने चीज़ों को enjoy करते हुए भी there is a lots of the learning to some serious things. So today I will try to take up to a journey to your hobby, and through this hobby to the astronomy. Philately is the hobby of stamp collection. I got this hobby, and I began this hobby when I was a child in my school, and then I used this hobby once I got in teaching. Then I used this hobby to propagate the learning, teaching, learning things with my students, and to incite them to learn the things while they enjoy the things. किताबें पढ़ना, लैब में जाना बड़ा मुश्किल बात हो जाती है. But एक हॉबी, एक टाइम पास के साथ में अगर चीजें सीख ली जाए तो कुछ उसका मजा ही अलग है. So stamp collection is the one of the world most popular hobby. We call stamp collection those who collect the stamp. Yeah, the hobby of stamp collection and the study of the stamps and the related postal material we call the philately. So I try to develop the astronomical aspect, the history of the cosmos through the postage stamp. All over the world, the different countries issue the stamps to commemorate the different events. Astronomy is one of the events which is commemorated by almost all the countries, whether they are doing the research work in that, whether they have launched the satellite or not. But every country in the world have issued this stamp. Through this stamp, we try to make this story. So let us have a quick journey to this. I will just go through a little bit about those who are not aware of this. What is a philately and what is its pedagogical effects? How we can learn the things through the hobby. Everyone has got some hobby. Hobby अगर नहीं है तो होनी चाहिए. As with my experience, with my age, I tell you, once you go in an old age, you find the hobby is one of your great savior. It helps you a lot because it is a time when you like to spend with something which you could enjoy. So develop the hobby, and you cannot develop the hobby in a day. आप सोचे कि अब जब खाली हो जाएंगे तब हॉबी डेवलप करेंगे, कोई ऐसा नहीं होता. It is a process which begin at your age. It may be the hobby of singing, dancing, painting, reading the book, anything, but must have some hobby. And how to make this hobby a learning experience, that I tell you the way. So, hobby of the stamps collection begin when the stamps begin first. When the stamps are issued, they were issued in the England in 1840. We got the first stamp of the world, the black penny, we call. They were the token. Before I just tell you a brief history, why stamps? टिकट क्यों इशू हुए? टिकट इसलिए इशू हुए क्योंकि उससे पहले जो लेटर जाते थे उसका पेमेंट करता था the one who received the letter, and that was a very tricky thing. लोग रिसीव करने से मना कर देते थे. So all the work, all the energy which is spent for taking the letter was going waste. you'll not get paid for it, right? और उन्होंने ये लोगों को देखा जो वर्क करते थे, उन्होंने ऑब्जर्व करा कि स्टैम्प्स की मतलब लेटर की कॉस्ट या उसकी नहीं है, लेकिन वो जो प्रोसेस होता है वो बड़ा कॉस्टली अफेयर है। तो उन्होंने तरीका निकाला कि अच्छा यू पे समथिंग, और वो टोकन जो आप पे जो भेजेगा वो पे करे, और उसका जो टोकन है वो आपके लिफाफे पे लग जाएगा, और वो टोकन रिसीप्ट वाज द स्टैम्प। तो इस तरह से पहला स्टैम्प ब्रिटेन में हुआ। देन इंडिया में ये रेड कलर का जो आप देखते हैं, दैट वाज अ ब्रिटल स्टैम्प, इट वाज इन अ सिन, इट्स कॉल्ड अ सिन द इन 1852। Official Indian stamp was the red one, half an anana, and after the independence, this is our first stamp with the tricolor. ये तो थोड़ा सा स्टैम्प का एक stamps, I tell you, this ambassador of the culture, they because they travel all over the world. हालांकि अब ट्रैवल करना उनका थोड़ा कम हो गया, बट यू विल सरप्राइज, डाक जाना कम हो गया लेकिन स्टैम्प्स निकलना पहले से ज्यादा हो गया, बिकॉज ऑफ द इंटरनेट जो इसको खत्म करने वाला है, जो डाक हमारी मेल सिस्टम को खत्म करने वाला है, उसी की वजह से स्टैम्प कलेक्शन बहुत ज्यादा हो गया। बहुत कंट्री नई तरीके से नई टेक्नोलॉजी से स्टैम्प इशू करते हैं, लोग वर्ल्ड में स्टैम्प कलेक्ट करने वाले ज्यादा बढ़ रहे हैं। वैरायटी ऑफ द स्टैम्प्स, तो क्योंकि ये दुनिया भर में जाते हैं, therefore every country try to depict their culture, their tradition, their history, their policies with the help of the stamps. So I have got the beautiful stamps of the world. टेक्नोलॉजी के साथ में स्टैम्प भी चेंज हो गए। We have got the crypto stamps. We have the stamps not from the common type जो आप rectangular समझते थे. It has got the different design, different shapes, different material. They are the stamps on the CD. They are the stamps on the leather. They are the stamp on the cork sheet. They are the stamps with the dust of the meteorite sticked on the stamp. So we got the variety of. There's the stamp with the crystals, Swarovski crystals. There's the stamps with the cartoons, with the friction films. This is the famous cartoon, Indian stamps issued on the famous cartoon. You know that cartoon? Are you aware? इन स्टैम्प्स की स्टोरी को आप जानते हैं या नहीं? बचपन में हम सब होने करिए, हमारे घर में खूब सुनाई जाती थी। Are you aware of this? Can you tell? किसकी कहानियां ये चार स्टैम्प? पंचतंत्र। Yes, they are the पंचतंत्र stories. All right. So that's what I want to say. Stamps की major change हो गई। क्या कर सकते हैं हम? एजुकेशनल बेनिफिट क्या है इनका स्टैम्प्स का? दे when you collect them, it gives you the patience, it gives you the persistence, because you have to collect, it takes a time. Then spirit of inquiry, once you arrange, अभी आपको लगेगा जब I will show you something, some slides, then how once you collect the things, then you are compelled to ask to know about कि इसमें है क्या, जब हम उसको अरेंज कर रहे हैं तो क्या चीज है इनमें। So this way we learn the things too, right? Refinement of our analytical skill, cultural value, network, global network. Once you once you are in the hobby, you are the part of the global network. You connect with the people of all over the world who have got the same hobby. So this is the trend nowadays in the every field. This networking is very, very, very important. Your academic is the one part. I'm also associated with the school education, where the student goes to the higher universities or the abroad, and in the abroad you will find that for the admission they take 1/3 weightage of your academics. The rest is 2/3 weightage goes to what extra you can do, how socially useful you are, how connective you are, how good networking you have, how much you can think out of the box. So these hobbies help you to develop, to get these traits, these skills. These are the some stamps issued by the India to commemorate its achievement in this space, right? Can you identify what is it? This one, sorry. But it's like, can you go back? Okay, we'll got something. Now, my story began the concept of the cosmos. I've taken the stamps, which in our mythology, what is the cosmos is there. Through the stamps, I try to show these things. Virat Sarup, which is the during the Mahabharata, Krishna shows to Arjun, and that was the first concept of the cosmos where everything, every time, every all aspect of the material of the living being, they all confined in a one body, that is the Virat Sarup. That is our first concept of the cosmos. So I begin my collection of the with this. Then we have the trilogy. That's Brahma, Vishnu, and Shiva, the one who create this cosmos. One, Brahma. This is the stamp issued by the French settlement in India before the independence. This is the stamp issue. This is the Nepal, stamps of the Nepal, where there you are seeing the Vishnu. Then Nataraj, cosmic dance, which shows the how the cosmos is get created and the destroyed and the recreated multi-universe. So this is then finally in our mythology we have the concept that the earth being taken out from Varaha Avatar, right? So that's how I take the journey of the philately of the cosmos in my collection. Then astronomy was a fascination for means even thousands of years before. Earlier, when the civilization started developing, people used to see the stars. They were afraid of the things. In the ancient, I have taken the pre-Columbian year, where there was some artifacts. Codex, Dresden Codex. Codex was our calendar which was there in the Dresden Museum of the Germany. It was from Mexican, American, pre-Columbian period. There they have taken the different aspect of the astronomy and the date deciding on the basis of the moon and the sun movement. And the interesting one thing is that this one, this big picture, this is a stamp. This is a stamp issued the history of the universe. This is in the desert of the Nes, Peru, where this type of the structure we find, which can be seen from the very high altitude. This structure of the bird and the insect, which is on the very large scale, now no one will be able to identify why these pictures are made at a larger scale. Then there is a very famous author. He has written a novel, Chariot of the God. He said that earlier, perhaps before our civilization developed, the God came from outside. I mean, God were the people, alien, which came from outside, and they need some identification or landmark, and they made these structures were made for them because their date back is more than 2,000 years, right? So this type of the structure we find, and the stamps lead you to know about these things. Then in China also, the astronomy developed. They first observed the supernova. They observed the supernova. They made the different instruments for detection of the earthquake, very sensitive, the direction. This one stamp shows a device. These two stamps shows a device to detect the earthquake. The little movement will make the ball to fall in the say some toads are there on it, and some then Islamic part of the astronomy has been developed. From the India, they have taken the various concepts of the mathematics and they developed the new theories of the mathematical theories of the space. Then Roman and the Greek period, it comes Renaissance. After the Roman and Greek period, there was a long gap. There was no astronomy developed because the Christians were not very much interested in developing the astronomy because it was contradicting to their belief, right? So it was a long gap, and after that gap, then Renaissance period when it comes, then the astronomy start developing. So I'm showing these stamps of that time, that period, which shows the development of the astronomy, the calendar, and astrology and astronomy. I've taken few stamps. Sometimes the astronomy was to be taken as an astrology. Astrology is predicting the future. It is, we don't call it science. Astrology is but that was predicting the future based on the stars. Earlier, after the Middle Age, this was very popular. Saint Thomas Aquinas of the Italy and the European Renaissance astrologers, they were all astrologers. They study the astronomy to predict the future, right? And even you will be surprised, the Kepler, whom we take it as a big astronomer, he used to have his livelihood by astrology, although because he cannot go against the church. So he used, beside his mathematical and the concept, he used the astronomy to predict the future of the king and the rich people over the nobility using the astronomy. So Kepler also, and the Nostradamus of the 16th century, very famous, but again he hid his basic idea of the astronomy, and he used the astronomy to predict the future, to save his skin, and to keep it in the good eyes of the church as well as the nobility. Then it was in Copernicus. I've used the stamps of the Copernicus. One cover stamps is not only the stamps, but these are the cover, postage cover from the Polaska. Polaska, Poland was a place where the Copernicus was born. So once you collect the stamp, you know about Copernicus, you know the place where he was born. Knowing the history of the science is also very important. Knowing the science is very good, but knowing the history, how the things develop, how the things are related, that also help you to lead, to create the interest in the science. So this cover shows the university and the city where the Copernicus was born and this time. Then Copernicus' idea was not accepted by the church, so they banned his book. It was banned. Work of the Copernicus was given in the index of the forbidden book, index of the Archeo Sagetta Metallico. That was where the book was banned and kept. Right? In 1660, it's only in 1993 is Pope Paul II, who say that no, we were wrong, church was wrong, Copernicus was right. So he's taken out his book, he accepted his mistake, church mistake, to ban the book of the Copernicus 300 years ago, and then release the book. And that was a pope who banned the book, Pope Paul V, who issued the order to ban the book. These are the stamps and the booklet of the stamps issued. So that is how the story goes. That's about the mechanical universe, quest for precision, the Newton work. I tried to show the stamps of the different astronomers who use the mathematics and the different devices to give the shape of the universe, the mathematical model of the universe. The telescope, the Galileo.
Was that stamp issued by Vatican or
Vatican.
Vatican?
Yes, Vatican. Then the biggest was the discovery was the telescope. Galileo used the telescope, although the lens was made not by the Galileo, still it is a controversy, but we accept that Galileo used the telescope first, and he observed the satellite of the Jupiter. He observed the crater of the moon. He observed the faces of the moon, and then he observed the faces of the not only the moon, sorry, but of Venus. And this all break the old Aristotle idea or concept of the universe, and this was a breakthrough for it. Tycho Brahe, he was earlier not accepting the theory of the heliocentric theory, but later on, once the Galileo showed him proving the things, he accepted the things. So that was a journey. I will try to cover up the things, our place, various pupil, Kepler's, Galileo work. Through the steps, I try to show that what was their work. These all the steps and their collections are for the display there in the lobby. So once you go out, you can go through these collections. You can find out this one and can get in some idea how your hobby can help you to develop the things there. I think it will take a long time, so we'll stop over here because our main point is, which is coming up, visit to the LIGO lab. That is the main thing. My purpose was only to encourage you to take your hobby and keep the learning process, make it as enjoyable as well as a learning tool.
दो अनाउंसमेंट था आप लोगों के लिए. अभी आप लोगों ने अटेंडेंस ली थी. तो एक कल के सेमिनार का आप लोगों को पार्टिसिपेशन सर्टिफिकेट आप लोग आएंगे मिलेगा ही. लेकिन आज का दिन, सर, if you permit, so today we will have a special certificate for this audience. आप साइन, योगेश जी साइन और यूएस से लीगो जो डायरेक्टर है वो तीनों साइन. तो एक स्पेशल सर्टिफिकेट आप सब लोगों के लिए हम अलग से बनवाएंगे for today's event, right? Those who have physically attended this. ठीक है? ब्रेक for half an hour. ये ब्रेक नहीं है, लेकिन आप लोग सर ने एक बहुत अच्छा डिस्प्ले नीचे लगाया है, उसको देखिए, घूमिए फिरिए. आफ्टर हाफ एन आवर लगे मीट, है ना? कोई ऐसा है जिसको लग रहा हो इसको स्टॉप कर दें, तो स्टॉप किया. वापस शुरू करेंगे ना, पॉज करना, डोंट स्टॉप. हेलो.
Hello, I can hear you.
Yeah, just a minute. I think we can also hear you, but you should be audible to the audience, which is, I think, a glitch we are facing. यहाँ से आ रही है वास्तव में. पहले क्या किया था? हेलो.
Yes, I can hear you, and I can see you too.
Okay, thanks. So now the audience, yeah, audience is there.
Hello.
There are two senior professors are also there with us. Professor P.C. Deshmukh from IIT Tirupati. He is also with us. Professor Deshmukh is just in the third row.
Very nice to see you.
Professor Yogesh Bhatnagar, he is also with us today. So now you can start.
Okay.
Thanks.
So as you can see, I am outside, and let me turn the camera. And what you see there is a very long beam tube. Actually, you don't see the beam tube. The laser travels in a vacuum tube for 4 kilometers that way. What you see is the concrete enclosure on top of it. If I turn around, you see the main building, what we call the corner building, that's where the laser starts. So the laser starts there, and it's split two ways. One way going behind us on what we call the X arm, and another, and let me turn the camera around again, if I can. So one, half the laser goes that way, 4 kilometers, and bounces on a mirror and comes back to the corner station. The other beam goes that way. You might be able to see the other arm that way. So it goes that way. We call that the Y arm, gets reflected on a mirror 4 kilometers away and comes back. And what we measure, we call this an interferometer because we measure the interference of the two beams when coming back to the corner. Let me introduce you to Gaurav.
Hello.
He's going to be helping us too.
Yes. Hi everyone. I'm Gaurav Varadkar. I'm a PhD student at IIT Bombay in Mumbai, and I'm visiting here for 3 months, which is about to end in a couple of weeks. So I'll be back. So yeah, I'm really grateful to Gabby for doing this, and yeah, we'll be talking about LIGO Livingston today. Yeah.
And of course, that reminds me that I didn't introduce myself. I am Gabriela Gonzalez. I'm a professor at Louisiana State University, and I have been doing research on gravitational wave detection of gravitational waves with LIGO since my PhD, and that was a long, long time ago. So I won't count the years, but I will give Gaurav the camera.
Yes. Right. Yes.
And then we can keep giving you the tool.
I hope everyone can hear Gabby still, like, because we are slightly away from her right now. Can you give me a thumbs up?
Me?
Oh yeah, awesome.
Okay.
Oh, lots of people. Awesome. Yes.
Great. So we were saying that in the corner building, we have a laser, we split it two ways, in the X arm and in the Y arm. Those laser beams travel 4 kilometers, that's a long distance, come back, and then they interfere. And if those two lengths of 4 kilometers, if those two arm lengths are different, then the interference will tell us how different they are. And that's why we call this an interferometer. What the gravitational wave does, when a gravitational wave is going through Earth, and it's going to go through Earth, it doesn't stop here, it just goes through, is changing distances. And it's changing distances in such a way that if it makes this distance longer, it will make that distance shorter. So that's how we use interference to measure the gravitational wave. The problem, and that's why Einstein himself thought that this was not going to be ever measured, is that the effect is very, 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 very small. The larger the effect, and that's why we have this interferometer that's 4 kilometers long. It's spiraling around each other, getting closer and closer and colliding and forming a bigger black hole. Most of the signal, because we are in Louisiana, and luckily the hurricane passed and it didn't do a lot of damage. So there's some water around, but that's it. The other LIGO interferometer is in the US, is in Hanford, Washington, in the middle of the desert. So the landscape is very, very different. And there is another interferometer that we take data with in Italy, that's called Virgo. There's another interferometer that's working on improving its sensitivity in Japan, that's called Cadra. But there's another one being built in India, in your country, a lot closer to you, and that's LIGO India, and we are waiting for it to be built so we can take data all together. So, in this tour, I want to show you next a prototype that we have of the suspension that we use, which the mirrors I mentioned that reflect the light to bring it back to the corner. are not just mirrors bolted to an optical table, they are actually big mirrors that are suspended in pendulums. So I want to show you the size of that and a prototype of those, that very sophisticated suspension. And then we'll go to the control room. But before that, let me know if you have any questions. And I love questions, so I hope I get some.
Yeah, I can see a lot of people thinking about what questions to ask right now. So yeah, if there are any questions, let us know.
We can answer those questions while we walk
while we are walking, we can answer some of those questions if there are any. Just while people are thinking of what questions to ask for, so this LIGO interferometer that you can see at the back here, it is 4 kilometers long, right? So you can probably make out there's a small white colored station here, which is far away and barely able to, like, I'm myself able to barely see it. So I'm not sure how much it is being transferred over Zoom, but that's not the end station. That's just halfway through. There's another 2 kilometers after that. So it's extremely long. And the other thing that we have here is that since it is like 4 kilometers long, when this site was getting constructed, they had to raise the last station a bit from the ground so that it accounts for something which is called curvature of Earth. So because of this 4 kilometer long distance, they had to lift it up from the ground a bit. And that was yet another evidence that, yeah, Earth is round. Yeah.
Yes.
So while we are going down, we have one more thing. Is there a question? I saw hand raised. Yes.
How to turn it out?
No, I don't need to turn it around. I'm just seeing if we can hear them. I don't.
We could hear them before. If you're saying something, we cannot hear you.
Yeah, a question is there. Now
yes.
Just,
Is there any special kind of mirror that is being used in the other side of where the light is getting reflected from?
It is regarding the mirrors which are used in the interferometer.
So if I understood the question correctly, is there a special kind of mirror that is used to reflect these lasers? Is that the question? Okay, awesome. Yes, non-verbal communication works much better apparently. Yes, thank you for raising your thumb. Yes, Gabby, you can.
Yes, the mirrors are very special, very expensive too. They are big mirrors of fused silica, which is glass, but it's a very special glass that doesn't dissipate energy, and that's very important. It dissipates energy very little, and that's very important because the more energy that the material dissipates, the more the atomic vibrations that we call Brownian motion will affect our measurement. So we are sensitive to quantum noise, to Brownian motion of the mirrors, and to seismic noise of the ground moving the mirrors. The mirrors also have a very special coating to make the mirrors. That's called a dielectric coating. And there's a lot of research on how to make those coatings lose less energy, because that is now our main source of Brownian motion. So the mirrors are very sophisticated, and we will show you the size.
Exactly. Yeah, we are going to see an actual mirror very soon. So yeah, we are just walking towards that. Meanwhile, at my back, you guys can also see that the corner station is there. Corner station where basically both the arms meet, like Gabby was saying. And you can also see a large cylinder over there, a small whitish, but it is fairly large. It's almost like almost two-storied building back in India. That entire cylinder is just liquid nitrogen. which is used to cool and like sort of calm down all of the optics so that your noise floor goes down further. And you can see that liquid nitrogen is used up every week, and we have to sort of replenish it, fill it back up every Tuesday. So there's like every week we close the detector for a few hours so that we can maintain all of these equipment. So we fill up these like liquid nitrogen. You can see that there's a lot of grass here, and if you cut the grass during the interferometer's operations, it was going to create a lot of fake gravitational waves, which you don't want to see, right? So what they do is they actually switch off the interferometer and then they do all of the grass cutting, which was something quite amusing to me when I first reached here.
Every Tuesday morning.
Every Tuesday morning is that.
Let me mention that the liquid nitrogen is not used to cool the mirrors. It's used to cool some vacuum pumps that we use to suck the molecules.
Yes.
We work at room temperature. In principle, if we could cool the mirrors, we would have less Brownian motion because the temperature is the motion of the atoms. But the problem is that we have very, very high power lasers hitting the mirrors and warming them up a bit. So it's very difficult to work with low temperatures, but that is something that the Japanese detector, Kagra, is doing. So now we will be entering what we call the Science Education Center. In this building, we do what we call education for not just students, but teachers. So we have tours of people coming here. And we have a lot of exhibits, which are toys, a fancy way of saying toys, but we won't be able to play with those because you're not here. But when you visit, hopefully sometime in the future, you'll be able to play with all the toys we have here. And these are just some of the toys. We have a room full of exhibits.
Yeah, that's the room that Gabby is talking about. It's like a huge hall with a lot of, it's basically their science center. So you have so many experiments which explain you different concepts of physics. At the back, you can probably make out a tornado as well, which is one of the live exhibits that we have. And yeah, overall, it's like extremely interesting.
These are all about vibrations and waves and interference, which are the basic concepts for LIGO. We also have a few medals in here, including a copy of the Nobel Prize medal that Ray Weiss had made by the Nobel Foundation for each of the two observatories. So we have a Nobel Prize here, the Nobel Prize medal.
Yeah, and we have one more guest with us right now. Yes, Devasmita.
I'm Devasmita. I'm a graduate student at LSU. I work with Gabby. I came here for the tour.
Awesome.
Great. So we were working to see the mirror prototype. We don't have an actual mirror because, like I said, the mirrors are very, very special and very, very expensive. So we only have those in the interferometer, and we have spares very, very well taken care of. But here,
we do have one older mirror, right?
Yes. In a previous generation, what we call the first generation of LIGO, we used the same facilities, 4-kilometer facilities, but we had a simpler setup that didn't give us enough sensitivity for detecting gravitational waves, but it was a proof of principle that we could operate an interferometer that was 4 kilometers long. And let me tell you, I was working at that time, and it wasn't easy at all. At the time, we use mirrors like this, and this is an actual mirror. This is one of those very special mirrors, and this is a 10-kilogram mass that is hanging from a single loop as a pendulum, And you see that there are some cables here, and that's because we glued magnets on the mirror, and we have electrons. At which even
Repeat the question.
Video is on, I think.
Length
Why the length is 4 kilometers? Is there any specific requirement for that? Or it might be
that's a good question. Can any of you answer that?
Yeah, I can. Okay, so the gravitational waves that we want to detect has a very small amplitude. It's in the order of 10 to the power minus 2021. And the thing we want to measure is the strain introduced by these gravitational waves, which goes over delta L over L. And delta L is basically the change in length. So if we increase the arm length of the interferometer, which is the L in the denominator, then we can detect gravitational waves with less amplitude which are coming from farther apart.
But why is it 4 kilometers and not? It's more expensive. Yes. So it was a trade-off between cost and sensitivity.
Yeah.
But there is a project to build a future interferometer that we call third generation interferometers. And in Europe, there are concepts with 10 kilometers length, in the US with 20 and 40 kilometers. So we will have longer interferometers in the future, now that we know that there are gravitational waves to be detected. We didn't know that before, but we knew, but we didn't know how many.
One more question.
Awesome. Yeah, I hope that answered the question. If there's any more question, let us know.
In the meantime, we'll walk to the control room, which to me is the most exciting room. Yes. But if you have any questions, we'll be happy to answer them today. And I hope you can or you can visit LIGO India once you speak.
सर आपका माइक और उसका माइक बंद करो आपके फोन का माइक और उसका माइक उसके बाद ही हो पाएगा ये रिपीट करेगा बार-बार
ये समझ नहीं पाया
माइक बंद माइक उनके फोन का माइक अभी भी चालू है यार
Yeah.
I would like to
Yes, we can hear you with some echo that I hope you guys are working at. But yeah, please feel free to ask us.
पीसी पे जा नहीं उसी पे जाना पड़ेगा रिपीट मारेगा वरना या फिर सर को बता दे तेरा क्या जो भी क्वेश्चन है नहीं यहाँ से नहीं होगा सर उसी से करना पड़ेगा
Okay, just
उसी का सर माइक ऑन करो ये बार-बार
if you want to type the question, that's also fine. We will be able to read it over.
Hello, can you hear my voice?
Fantastic. Yes, we can hear you.
I want to ask, this observation are taken in inertial frame or non-inertial, because Earth is ultimately a non-inertial frame. So
the question is, are the observations inertial or non-inertial?
Well, we are on Earth, and Earth is rotating, so Earth is a non-inertial frame. But we take all of that into account. We don't say very small perturbations on how we take the data. The most important thing is to compare the data from two interferometers. So to know where the gravitational is coming from, you look at the time difference between the signals and the phase difference of the signals that are measured at two interferometers, and that can give you an idea of the position in the sky. But that's also why we need many interferometers. With two interferometers, you can only locate the direction as a wing in the sky, half a wing if you look at the phase difference. With three interferometers, you can triangulate. With four interferometers, you can triangulate a lot better and get more information. So that's why we want many interferometers around the world, and that's also why we all work together.
But somehow it will create some disturbance and error also, no? Because it's a non-inertial, but we are taking an inertial frame observation.
Will it create any perturbations because we are in a different frame of reference?
No. Well, you have to take it into account when you do the general relativity calculations, but they are very, very small because we are all in the same non-inertial frame. And what matters is the relative differences between the different detectors.
Thank you.
Awesome. Those are some great questions. Keep them coming towards us. We'll be more than happy to answer all of those. So what we are doing now is we are entering from that way. We are entering the main building of the observatory, which you can see where we have all the corner stations, most of the offices where people and detector engineers sit. So you can roughly make out that the detector arm was coming from that side and it is going to enter this building, and we are also going to enter that.
These taller walls are the experimental area. So we have the mirrors that we showed you are actually hanging inside vacuum chambers. Those are very tall vacuum chambers that also have their own seismic isolation systems. So, like I said, it's all very sophisticated. We will not get close to the experimental area. We will only go to the control room because we're taking data. That's why we're talking, because we're coming 2 or 3 a week.
Yes.
And it's only 8:30 in the morning here in Louisiana, but it's already getting quite warm. We are enjoying the air conditioning inside. This is where the experiment is, and that's where we are not going to go. We are going to go to the control room.
Yeah, that is where all the good stuff is. But we are going to look at the mission control room. Yeah, no? Yes, that's something we can see inside.
This is the Nobel Prize poster. And the Nobel Prize was awarded in 2017 to Ray Wise, Kip Thorne, and Barry Barish. Ray Wise and Kip Thorne started in the 70s with this concept of a kilometer-long interferometer to detect gravitational waves. They convinced the National Science Foundation in the US to build the LIGO interferometers in the late 80s. They began construction in the early 90s. And it wasn't a while until we measured the first gravitational wave. But we did it. This is a schematic of what we were doing.
Okay, yes.
Is there a question? So this is a schematic of the vacuum system. Of course, this is 4 kilometers long, so it's not to scale. But this is the corner station. This is one vacuum chamber. We have another similar vacuum chamber at the end, and the light goes back and forth between those. And same in the Y-arm, back and forth. They recombine here, and then they come out, and we have photodiodes at the end that measure the interference. We're almost there. we are doing a virtual tour. So you have an audience, an online audience here. This is Ed. He's the operator in charge today.
Hello.
She is actually operating the detector, which means it's making it work. And it's working. We can tell it's working because if we look at that blue trace in there, that blue trace, it's a live measurement of the noise in the detector. It's not a measurement of a gravitational wave. To find the gravitational waves, we have computers that use programs to look into the data that is produced by the detector. But this is where we monitor the noise of the detector. And if you look at, again, the blue trace, you might see it moving a bit, and that's, again, because it's a live measurement. And if you can tell the numbers on the left, you probably cannot, but I'll read them to you. It's 10 to the minus 23, 10 to the minus 22. That is the ratio, what we call the strain. That's a ratio of the difference in length between the two interferometers divided by 4 kilometers. And now let's see how good your algebra is. If we look at 10 to the minus 23 and we multiply that by 4 kilometers, what change in distance do we have?
It's 10 to the power minus 20, around that range, that order. So almost 1,000 times less than the radius of a proton. That's very, very small distance. That's why you need it to be very sensitive.
It's a lot less than 1,000 of a proton. So we are measuring some nuclear differences. However, let me, and you should say that's impossible. And it is possible. I showed you the live graph. But what you can also see is that the blue line is actually that low at some frequencies. The x-axis in that plot is frequency. And you can see that between 100 and 1,000 hertz, that means waves that have 1,000 cycles per second to 100 cycles per second to 1,000 cycles per second, those we can measure very, very well. And those are the waves produced by these merging black holes. But at lower frequencies, we have very poor sensitivity. The noise is a lot larger. So we cannot tell that the difference in length is less than a proton diameter today as opposed to yesterday. We can only see that if that distance is oscillating many times per second. So that's why if you want to see signals from the big black holes, the ones at the center of the galaxies, those produce signals that are much lower frequencies. So you need something that's 1 million kilometers long. And we cannot build that on Earth, but there's a project building that in space. It's called LISA, and that's going to launch in the 2030s. The other thing I want to show you is how we can convert the noise into a distance, how far away we can detect the signal. And we use a distance, the distance is different depending on whether we're talking about neutron stars or black holes, or whether we're talking about black holes of different size. The larger the black hole, the farther away we can see it, but the larger the black hole, the lower the frequency, so sometimes it goes out of band. So we use neutron stars because neutron stars have about the mass of the sun, 1.4 times the mass of the sun each star. So they are always, the signals are always in our band. We have only detected 2 mergers of neutron stars so far, but I'm really waiting for the next one. And this metric is telling us how far away we can see those signals with a signal-to-noise ratio of 8. And the blue trace is the distance in megaparsecs, so the y-axis you probably cannot tell, is about 100 60, 170 megaparsecs. So that is like 500 million light years. That's how far we can see mergers of neutron stars. But you see different colors in there. So blue is Livingstone, red is Hanford, and you can see that it's about the same. Pink or magenta, lower at 40 or 50 megaparsecs, that is Virgo. So we are taking, and you can see that the sensitivity goes up and down, and that's our sensitivity to disturbances in the environment. And sometimes it goes to 0. That's when we say we lose lock, which means we cannot push the mirrors enough to make the light go back and forth and keep constructive interference. Sometimes the ground moves too much. Sometimes we don't know what happens, but usually if the ground is moving a lot because of an earthquake, we don't have earthquakes here in Louisiana, we have hurricanes, and we actually shut down the interferometer so that we wouldn't have trouble with a hurricane. But we don't have earthquakes. But earthquakes almost anywhere in the world will make the Earth, the whole Earth, move around, and that will affect us.
And there's a way in which we monitor these earthquakes somewhere over there. So if we move towards these screens, so when we entered this control room, you probably saw the number of screens that were there. Any guesses at the number of screens that are there in this control room? Yeah, it is above 30. So all those screens tell you something extremely important about the observatory and the interferometer. So for example, the discussion that Gabby was just having, which was to understand if earthquakes and other quite stable now they are. And then the last screen here is what we call as human activity. So you can see that we monitor all human activity in the sense of their seismic noise that it is creating over in different parts of our interferometer. And essentially if you're driving a car at large speeds and if you brake, that is going to cause seismic vibrations which are going to affect our interferometer. Is that right? And yes, you can see that there's a big yellow peak, which I don't know why that is.
That's because of the train. There is a rail track that passes near the wire, and they increase the seismic motion a lot.
Okay.
And it used to cause us trouble. Now, not so much.
So you can see about 4 hours back, there was this huge spike, which was from the train motion. And yeah, this is about the noise.
Something else that might be interesting is looking at the top 2 screens. That's the light that is scattered towards the camera that's looking at the mirrors at the end Y station and the end X station. We call those end test mass ETM, so ETMX and ETMY. And if we see a lot of light in there, that's because we have light going back and forth in the arm, having constructive interference. That means we are in low. And that means that we can detect gravitational waves. And finally, the one thing that I always like to show, and I might turn on the light. Are all these pictures on the wall. Those are pictures of the inside of the vacuum chambers. And that's a quadruple pendulum with a real mirror. That's a picture of the real mirror hanging in there. And in some vacuum chambers, we only have a quadruple pendulum and some instrumentation around it. In some other chambers, we have a lot of other optics that we need to get the signals on the photodiodes and to stabilize the laser and to make the interferometer as sensitive as we need to. So that those pictures give you an idea of how sophisticated this instrument is.
And I can see someone asking, do we permanently have one person sitting inside the tubes who is monitoring the interferometer? That was a question that someone asked. I can see at the back.
Of course not, but you might also see that every picture that has a person, and these are people that are installing the mirrors and the hardware inside the vacuum, they are all wearing what we call bunny suits. And that's because we need to avoid contamination of the mirrors. Because if the mirrors are contaminated, then they lose more energy, and we are more sensitive to the Brownian motion of the mirrors.
That's awesome. Yes. If there are any questions at any point, just raise your hand, please, and let us know. But yeah, you can see that all of these photos at the back as well. So most of them are not clear in the video, but they are essentially showing all the optics that are inside these big access modules that we have. And yeah, this is the control room for you.
That's great. Thank you very much. If there are any questions from any present here. So now I request Professor P.C. Deshmukh sir for the concluding remarks and formally giving thanks to you, all of you. Three of you rather.
Great. So thank you all. Thank you all for the interest on visiting, at least virtually, LIGO, and I hope you enjoyed the visit.
Yeah.
It was awesome. It was absolutely awesome because the kind of laboratory that you're working in, 4 kilometers one way, another 4 kilometers on the other way, and measuring distances which are the fraction of the size of a proton, this is absolutely mind-boggling. Thank you very much for giving us a tour of LIGO. Yes, we have certainly seen the photographs, but never had such a detailed view of your setup over there. I know that now we are completing like 9 years of the first detection of gravitational waves. How many such events have been detected at LIGO?
More than 100.
More than 100? Wow.
Yes.
In the third observation run, there were 90 confident detections, and in the first half of the fourth observation run, we had 81 confident detections, and the second half of the fourth observation run is going on right now.
Do you know any time if such an event is coming up, and do you have any means to predict when you may see the next one?
We don't. We have an average rate at which we can detect these events. And like I said, there are 2 or 3 a week. But we cannot, at this time, we cannot predict exactly when they are coming. However, there is a project. There is an idea that when this space detector called LISA is flying, they might be able to be sensitive enough to the signals from the smaller black holes, the ones that we detect, and they would see those signals much before the coalescence that we see. So they would be able to predict those and tell us, make sure you're on, because like you said, like you saw, we're not always on. So make sure you're on to detect these gravitational waves. But that's going to take a while.
And these 100 events that you have detected so far, do they come from, are they sort of isotropic? Do they come from roughly evenly distributed from with respect to Earth, or are they from any specific region?
Well, for most of them, we don't have a very good localization because we need 3 detectors running with good sensitivity to have good localization. But from what we can tell, there is no preferred direction.
Yeah, I would hope so. I would certainly hope that.
And
Thank
for
you very
exactly that reason, you need a really good localization, which is where exactly you will have LIGO India playing a crucial role in the future, when it will be able to narrow down the localization area almost by 50 times in certain cases. So things like answering questions like exactly the one that you asked is something that LIGO India will definitely answer in the future.
We cannot even localize a galaxy where the events happen. For the neutron star coalescence, for example, we had the best localization so far. That was in 2017 because we were taking data with Virgo. But we localized it to an area of about 30 square degrees. And there were 40 galaxies at the distance. We can more or less tell the distance at which the event happened from the amplitude that we measured here. So at that distance in that area, there were about 40 galaxies, and astronomers had to begin checking each one of those galaxies to find the one in which there was a bright spot that had not been there before.
So these EM counterparts to gravitational waves is what we are talking about. So apart from the gravitational waves that are given by these neutron star mergers, you'll also have a lot of X-rays, infrared, optical, and even radio waves coming from these sources if they are oriented in a particular direction towards us. And which is why we need to point our telescopes towards these patches of the skies, because LIGO can tell you that, gravitational wave was detected, but then you need your telescopes on ground and in space to point towards these, which is why the localization and the number of galaxies like we are talking about is quite important. And again, LIGO India and other future missions will definitely help us out here.
And in terms of light years away where these events have taken place, do we have an estimate of what is the closest event we have seen and what is the farthest event we have seen?
The closest event has been that binary neutron star merger that was 30 megaparsecs away. 40 megaparsecs away, yes. And the farthest away, I don't remember now, but it's close to gigaparsec.
Much more than that. We have had almost 8 gigaparsecs.
8 gigaparsecs, okay.
Yeah.
See, I lost count.
Yeah, that's a huge range.
They are still what astronomers call the local universe, because the redshift is still very small. I mean, it's less than 1, so or close to 1, but not that far away, so that we can make cosmological consequences.
So thank you very much, Professor Gabriel, for a very exciting event here. There are a number of young scientists coming up, young students, and I'm sure that many of them will be very inspired to take up further studies in this field. I would like to thank the 2 young scientists with you who are there with you.
Yes, Gaurav and Devasmita.
Yes, I have to confess that I did not get their names very clearly, but perhaps you can send an email to Professor Yogesh Chandra and we will like to thank them individually also. So I want the names and email addresses of both the young scientists who are with you. Very, very proud of all the excellent work that your team is doing. So thank you very much, Professor.
Yeah.
Yogesh.
Thank you very much. But before logging out, we would like to have a group photo. So I request all of the participants come to the.
I'll just go this way, just so that my hand does not take more.
So it will be a virtual tour as well as virtual group photo.
Yes.
Okay.